Good morning, all of you. Welcome to our session of today's lecture, which is on the history of Indian astronomy by Dr. Mayank Vahia. Vahia sir is um, a retired professor of astronomy. He was doing excellent work at the Tata Institute of Fundamental Research, Mumbai. And Vahia sir is a veteran in this field, and I will give a brief introduction about him. Um, he had a wide area of interest. Vahia sir was involved in 7 satellite missions where telescopes were placed on American, Russian, and Indian satellites. Vahia sir also participated in experiments such as Anuradha that was flown on the space shuttle in 1985 and Indian X-ray astronomy payload which was flown on an Indian satellite in 1996. Sir participated in the solar X-ray spectroscopy experiment that was launched on India's GSAT-2 satellite in 2003, and he was also involved with AstroSat, India's most ambitious multi-wavelength astronomy satellite. And Sir also was interested in particle acceleration in solar and stellar flares, the gamma ray bursts, uh, and Sir is a member of many of the societies like Indian Physics Association, Astronomical Society of India, and Archaeological Society of India, and many similar societies. And especially his interest in Indian astronomy is of praiseworthy, and he was also one of the founding members of Indian Astronomy and Junior Science Olympiad programs in India. For the past 20 years, he was much interested in the history of Indian astronomy, and Sir is a well-known science educator and communicator, and we are fortunate to have him at Solapur Science Center for today's popular science lecture. Today, Sir will deal with the history of Indian astronomy and especially the growth of astronomy, which was a gradual process throughout the years, and how it was nourished and enlarged in the due course of time. He will also trace uh, how these astronomical evolution happened all throughout the time, and how mathematics, contribution of mathematics also changed the field dramatically. And I will now welcome Vahia sir to deliver the lecture.
Yeah, thank you very much, sir, for your kind introduction, and I'm grateful to you for this invitation. It's my pleasure to deliver this lecture to you. So, first, let me share my slides with you.
Yes, sir.
Okay, so I'm going to talk about. Can you see my slides?
Yes, yes.
Uh, So, I'm going to talk about origin and growth of astronomy in India, starting with prehistoric period, and I will not cover any aspect of modern astronomy, but I'll certainly cover aspects of how astronomy started. So, if you think about it, archaeology will only tell you how technologically sophisticated a culture is, what they could make, what kind of machines they could make, what kind of technologies they could make. But it is very difficult to know what they were thinking, how they were working, etc., just from archaeological data. So the cultural data, the intellectual growth, their myths, their religion, their literature, etc., cannot be deciphered from archaeology alone. For that, you need to know something more about them. And astronomy is one of the instruments that tells you that how much science is in you, in the sense that how many of astronomical observations they made will tell you how sophisticated the culture was. And mathematics becomes an integral part of astronomy, as we will see. Together, they give you an independent window about what that culture looked like. If you look at astronomy, very early human beings realized that Mother Earth is the one that gives life, and Mother Earth gives life only when there are rains. So the idea of Mother Earth and Father Sky is probably predates humans in the sense that probably other like Homo sapiens, like Neanderthals, etc., also probably had some idea, beliefs like these, where the Mother Earth and Father Sky was there, because they also buried their dead in the womb of the mother for presumably for rebirth. So Mother Earth has to be shielded by Father Sky is a very old idea and earliest religious myths. Then, of course, there's a question of drama of thunderbolt, storm, the moon, the sun, the eclipses, the rainbows, and the meteors. All this add to a rather fascinating story about the sky that we create, and therefore we call it heavens, we call it the place where the gods live, and so on. Then sky has stars, and those stars are apparently a random distribution. But in order to help you with memory, you can collect them into various patterns, and you call them constellations or whatever you want to call it, in order to help you remember those patterns. And the nice things about these patterns are that they are constant over one's lifetime, and they do not change. And that is an advantage we would use to keep track of a few handful of elements that actually move, like the planets move, the moon moves, the sun moves, against this background which is completely stable. So you can use that to determine the periods of movement of sun, moon, etc., and so on. And we'll see how that works. We give stars names of famous people, famous stories, create mythical stories, put them in the sky, imagine stories in the sky, and so on, using this pattern that we make. We also have this idea of cosmogony. So what I have here is a rock art that is from Kashmir, and this is a rock art that is from Hampi, one of the caves near Hampi, and this is the drawing of that rock art. And you can see this drawing of this rock art shows you that there seem to be open circles here, there is this mounted circles here with these dots, and then there are lots of lines which are not symmetrical to this. There seems to be some kind of a ladder, and there are waves coming out which are not symmetrically connected. So they go beyond on both sides. And then there is also apparently a person who is presumably dead over here, and then there are various patterns that come. And one could, while it's difficult to know what exactly they meant when they drew this, but the idea of somehow connecting death, life, and sun and stars seems to be quite implicit in this kind of idea. And this is, of course, a very classical picture of a very early rock art where the imagination is that there is a superhuman who is controlling the movement of the sun and the moon, and that is a great god of heavens. So, myths and astronomy are closely associated, and their interrelation is a fascinating subject. However, we will talk only here about the development of astronomy and not so much about its manifestation in other ideas. Evolution of astronomy is not so easy in the sense that it did not begin with Galileo, and it was not that before that we had no idea about the sky. The idea of sky and the studying of heaven actually gradually rises from the earliest period of human history. So who needs astronomy? Lots of people need astronomy. Artists love astronomy because of the kind of patterns that you can make and the kind of designs you can do and so on. Farmers need astronomy because they want to know when the monsoon will come and when they should start sowing the seeds and so on. Travelers can use astronomy for traveling from one point to another using the stars, and we'll see how this is done. Calendar makers, of course, need to know full moon and new moon and so on so that they can keep a track of the skies. Priests need it, of course, for determining the exact time of various rituals, and therefore they need to know time. And astronomy gives you the best clocks. And in fact, even if you make a terrestrial clock, eventually it has to be synchronized with the skies. And astronomers need it because they're curious about the star, the structure of the stars, the designs of the stars, the movement of the planets, and so on. So a whole bunch of people need astronomy. The basic concepts of astronomy are not very difficult to grasp. So you can imagine, you realize that there is the sun and the earth goes around the sun in a slightly elliptical orbit and so on. But the axis of the earth's rotation is slightly tilted by actually about 23.5 degrees. And therefore, when that axis is facing towards the sun, there is a lot more sunlight over here and we get spring. And when we get spring, the southern hemisphere gets autumn. When the pointing is exactly in against the sun, then you get summer in the northern hemisphere, winter in the southern hemisphere. Then comes autumn when the axis is again along the plane, and you get autumn on the in September you get autumn in the northern hemisphere and spring in the southern hemisphere. And then as you turn and complete your 1 year, when the axis is now pointing exactly in the opposite side direction compared to summer, you have winter in the northern hemisphere and the summer in the southern hemisphere. And this cycle goes on. So this is the basic idea that because of the inclination of the axis of the Earth, you produces its own dynamics. So we have monsoons and so on. But this is not how our understanding began. Our understanding began in a rather obscure manner. Just to look at the same figure again, you have the Earth over here, the axis of rotation is over here, and then the Earth in winter the sun will come into the sky and remain for a shorter time. In summer, it will remain in the sky for a longer time. So we get a picture like this. So if you look at the sun seems to rise in the east, somewhere in the east during the year, and set somewhere in the west. But during winter solstice, when in fact the northern hemisphere is facing away from the sun in June, sorry, winter solstice in December, when we have winter in the northern hemisphere, the position of the sun is that it rises at the southernmost point in the southernmost point in the eastern direction during 21st December. It remains in the sky for a very short time and then goes down again. On there are 2 days of the year when the sun rises exactly in the east, sets exactly in the west, and then interestingly, over the entire Earth, you get a 12-hour day and 12-hour night, even at the poles. Then, as the sun goes further north, the sun rises to the north of east. It remains in the sky for a much longer time, and we have summers because a lot of heat of the sun comes to us. And then we have, of course, the winter solstice. And the axis along which this happens is the North Pole, the rotational axis of the Earth. So in winter, the sun remains in the sky for much shorter time. In summer, the sun remains in the sky for a longer time. And then there is this equinox day. So you can imagine this equinox day are very important. And the point when the sun is over here and will start returning is a great day of great celebration. So that is Uttarayan, or December 21st. And similarly, when the sun is over here in June 21, it will start going back in the opposite direction. So it will start becoming cooler, and that is called Dakshinayan. So we get a movement of the sun from the sunrise point from south of east to north of east and back to south of east, with 2 days where we have exactly 12-hour day and night. Then we have the moon. We have the moon, and you know that if the sun is coming from the left side, then the moon looks like this. This is the moon. When the sun and the moon are together, you don't see the moon, and therefore you get new moon. As the days progress, then you can see partial. As the moon moves away from the sun in the sky, you can see it partially, and you get a waxing moon, and it keeps on waxing. You get first quarter waxing moon, and eventually, when it is exactly opposite the sun, you get the full moon, and then the cycle goes back of the waning moon. So we have a 27 and a half, 29-day cycle where the sun goes from full moon to full moon, or new moon to new moon, depending on what your choice is. But essentially, you have a lunar month, which is 29 days, 29 and a half days. That is the next concept. Then, of course, if you keep looking at the star pattern at the back, you notice something interesting. So in January, for example, the sun seems to cover the constellation of Scorpius. Sagittarius. So you can see Scorpius, you can see Capricorn, but you can't see Scorpius. And then in May, you can't see Aries, because you can see Pisces at the sunset and Taurus at sunrise, and you know that the sunrise has happened, but you will not see Aries. So you say the sun is in Aries. Similarly, in September, the sun is in Leo. May, the sun is in Aries. January, the sun is in Scorpius, and so on. So you have these 12 special constellations that we call zodiacal signs or rashis, which the sun visits one per month. By the time it completes one full rotation like this, roughly 12 full moons have occurred, and therefore we say 1 year consists of 12 months. But there's a problem, of course. The moon's cycle is 29 and a half days, so it completes 1 year in 354 days. We know the sun completes 1 year in 365 days. So there is that 11-day gap, and that has to be filled up and all that. So there are issues like that. But in general, this is what you see. You see the sun in different constellations. Divide that into 12 parts because 12 full moons bring the sun back to roughly the same position in the sky, and so on. Then there are eclipses. There are seven wanderers: Mercury, Venus, Earth, Mercury, Venus, Mars, Jupiter, Saturn, and then sun and the moon make it the seven. And then if you go to a temple, there is Navagraha because Rahu and Ketu are also considered dark planets, and we will come to those issues in a little while. Then you have comets, and you have shooting stars and so on. But the interesting thing about Earth that we don't normally notice, or which is rather subtle, is that the Earth is not spinning like a good boy in the sense that the axis of rotation is tilted by 23.5 degrees. So it is like a badly spinning top, and this 23.5 degrees tilt means that this axis points to different directions over different time. So today it is pointing to Dhruva Tara or Polaris. 3,000 years ago it was pointing to Thuban. Very soon that axis of rotation will go off moon, so already off Polaris. So if you look at Polaris very carefully, you will see that Polaris now also moves in the sky. And then 14,000 years from now, you will have Vega as your pole star, and this cycle goes on. So this is a 25,000 year old, 28,000 year periodic rotation of the Earth's axis, which actually is a very useful thing. Because roughly over a period of 1,000 years, you will very distinctly see that the sun has moved to a different constellation. The equinox point has moved to a different constellation, and that has been a very useful clock to determine various things. So, because of this precession, suppose if in 10,000 years ago, the vernal equinox was in Leo, that is the day on which you had equal length of day and night, the sun would rise in Leo. 6,000 BC, that was in Canis Major, that is close to Taurus. Today it is in Pisces. So for 2000 BC, it was near Pleiades. 4000 it was before Taurus, and so on. So depending on which period you are talking about, the sunrise point at vernal equinox would change with respect to the background stars, and this has been noted right from at least 2000 BC onwards. We have very clear statements. So there's a statement in Rigveda which says that the Pleiades will never change. The Dakshinayana is also can be documented. In 10,000 BC, around 10,000 BC, it was in Ophiuchus or near Scorpio. 5,000 BC, it was in Virgo, and today it is in Gemini. So this point of deflection actually are well noted in ancient literature. The easiest way of doing this observation is to put up a stick in the ground. And just a stick in the ground is so important that it is called a gnomon. And in fact, if you notice, all well-made temples have this gnomon in front of them. It is called Dhajastamba or whatever you call it. And you think it is meant for flying a flag. It is not. In fact, its original idea is that you determine the directions in the local geography based on the shadow of this stick. And the way the stick works is this. This is for Mumbai. You can imagine the stick is right in the middle of this picture coming out of the board. Then during winter solstice, when the sun rises over here, the shadow is over here. And over the period of one day, the shadow will travel all the way over here. At summer solstice, the sun rises over here, so the shadow is over here. And so the summer solstice shadow will travel like this. And between winter and summer, this solstice shadow will keep dancing. If you are in a region where the latitude is more than 23.5 degrees, in fact, the shadow will come much more inclined and will in fact not cross the center. You imagine what happens when it crosses the center. When it crosses the center over here, essentially the sun is right overhead to you on that day. And that is the day when you will have no shadow at noon. And in Mumbai, we have 2 no shadow days every year when the sun is passing through exactly overhead. But in northern hemisphere and southern hemisphere, you won't get that. You will get so 23.5 degrees above, more than 23.5 degrees north, you will not get 0 shadow days. On the other end, all your building shadows will always be towards the north, and the shadow will never come to the south. Similarly, if you are below the tropic of Capricorn, then you will never see the sun up overhead. Your shadows will always be towards the north, and the sun will always be towards the south. So what essentially happens is that you have the sun here which moves in this direction, the shadow moves in opposite direction, and that is how you determine these lines of shadow. Um, Several time units come from astronomy. Hours is one obvious one, days is another one, a week is another one, fortnight, which comes from whatever. So Krishna Paksha and Shukla Paksha both are roughly 15 days each. The month comes from the sun and the moon. The year comes from the sun or the moon, depending on your choice. 5 year period comes from lunar and solar cycle synchronization, and that is a very important period in Indian calendar. We call it one yuga. One yuga is 5 years, during which you must add two adhik masas in order to synchronize solar and lunar cycles. And then you get 19 and a half year eclipse cycles, in the sense that the eclipse patterns will repeat every 19 and a half years. It is called Saros cycle. Then you have 60 years cycle when Jupiter and Saturn will meet in the same constellation in the sky. Saturn's period is 12 years and Jupiter's period is 5 years. So Saturn will certainly meet Jupiter every 5 years, but it will meet in the same constellation every 60 years. Then precession, like I told you, gives you 100-year cycles. The challenge, this knowledge was not acquired immediately as we started looking at the sky. It took hundreds of years of effort and all kinds of technology to understand how all these numbers that I just casually told you. And cultures require to mature to that level in order to be able to give you that kind of information. To simplify how exactly this pattern happens, we define four different distinct phases of astronomy. The first is an initial phase where we note the relations between the sunrise and sunset. Then there is settlement astronomy, where we track the movement of seasons and stars. The astronomy of a civilization is far more sophisticated. Some astrology comes up, some cosmogony comes up. Ideas about who we are, where we are, why are we here, and so on. And then the fourth and final stage is technology based astronomy, which is the modern astronomy. In India, that starts by 500 BC, when the state supported students and teachers learn astronomy as a full time occupation. By knowing how sophisticated a culture is, you can determine its astronomical knowledge, or by knowing its astronomical knowledge, you can determine how sophisticated the civilization is. So let us begin with stage one. The first thing you notice in stage one is that the sun does not rise exactly in the east. This is summer solstice to winter solstice. The north or the west is on the left, and you can see that the sunrise point drifts over a period of 1 year and comes back again. And this is the first thing you notice. So if you have a window in the house, you will see that the shadow is not in the same line every week or every month, but it gradually drifts into a one cycle, and that is the first thing that human beings would notice. So we identify the sun as the source of warmth, life, and light, um, and then we realize how crucial the sun and the rains are to giving life, and sky rejuvenates the earth and creates great imagination in human mind. Because of the elegance and importance of the sky is also the abode of the gods, and we also mark this with the first arrival of rock art. Settling down begins the first generation astronomy, where people are fascinated by the sky and draw the images in the sky. I already told you there's a picture in Kashmir in a place called Likse, where you can see this great sun and the great human controlling, or the great god controlling the sun and the moon. Then there are interesting drawings. So this is a drawing that we found in Kashmir, dated somewhere before 2000 BC. And we obviously don't have two suns in the sky. And the moon is invariably much weaker. And if the moon is so close to the sun, it is nearly heading for a new moon, and therefore it would not be so bright. So our argument was that this was some strange phenomenon. And if this is a strange phenomenon, the only thing that can compare that daytime sky in brightness is if there is a supernova that has gone off sufficiently close to us, so that even during daytime it is visible and it is comparable in brightness to the sun. So you immediately say that if this is a supernova, then the supernova should have gone off between 2000 and 10,000 BC, because that is the dating of the rock. It should have been close to the path of the sun, the ecliptic, and it should have been as bright as the sun or the moon during its peak of explosion. And fortunately, what happened is that these exploding stars leave the residue which can be seen for thousands of years. So there is a supernova that went off in 3000 BC, which is called HG9, which exactly happened, which had which was brighter than the moon in the night sky, but not as bright as the sun, but certainly brighter than the moon. And it was exactly, so this is exactly the east. So it would be in the east. This would happen, and we saw the only one supernova at G9, which is close to the path of the ecliptic, and which would have been as bright as the at least the moon to be visible during daytime, is what we were looking for, and we found only one example. When you plot that example, it turns out that the rest of the picture fits very nicely with the other constellations. So you get this as Orion, Taurus, and Andromeda is over here. Pleiades is somewhere over. You can clearly see that this is not just a casual drawing of art. It is the oldest recorded observation of a supernova dating back to 3000 BC in the constellation of Taurus, just to the right of constellation of Orion in the sky. And this entire sequence is the picture of the eastern night sky when the supernova at G9 went up and became as brighter than the moon in the sky, and impressed the ancient artists so much that they actually drew down the whole sequence. So we have the oldest recording of supernova dating to 3000 BC in Kashmir. Then you come to second stage astronomy, where large structures are created with astronomy in mind, because now gnomon as a simple single stick is a potentially source of error, especially if you're using something trees can decay and so on or die, and therefore they use stones to mark the position. And before they came up with compact sundials, they had more elaborate ways of doing this, and I'll show you the examples. They probably start recognizing the moon and the way the moon's movement is studied. Constellations were certainly defined. Zodiacs were defined in Europe and adopted by everyone. In present-day Iraq, in Mesopotamian region, and were adopted by everybody. And nakshatras, which are very classically Indian studies of the houses of movement of the moon. So zodiacs, nakshatras, constellations get defined, eclipses are noticed, and attempts are made to determine their periodicity. Transient events such as comets get recorded at this time, and then new myths are created about the sun and the moon. So eclipse, typically the oldest myth is about Rahu and Ketu eating up the sun, and so on. These ideas come up from around this time. And first cosmogonical ideas about who we are, where we are, etc., begin to appear at this time. Megaliths essentially means large structures that are created using stones. Mega means large, and lithic means made of stones. So you get these large stone structures designed to keep track of the sun and the moon, and therefore the calendar. Megalithic structures are gigantic, and I'll show you some examples. And because they are so large, so for example, we know one example where the stone is 3 meters tall and just 25 centimeters thick. Now, if you want, and it is pointing exactly in the east-west direction, and if that is the kind of stone you have, a thin stone which exactly is pointed north-south direction, obviously you have to put it down centimeters thick, which was carried from some quarry we suspect is about 5 kilometers away, brought and buried in the ground, so that half of it is underground and half of it is above ground, because it would allow you to keep track of the sun. People spent enormous resources in making this observatory. In Western context, for example, we know Stonehenge is an observatory. In southern India itself, there are something like 2,000 megalithic structures, and we suspect that a lot of them are astronomies. We studied two, and we found that both of them are astronomical in their context, and I'll show you the example. So this is a place called Baise. It's about 100 odd kilometers from Manipal or Udupi, and there you have large stone structures. You can see this boy standing here with this 2 meter rod, and you can see that the stone is even longer than that. There's another stone which seems to be appearing smaller. It is less than a meter, but that is because the top part is broken, and you find it just behind this tree, under this tree, as the second part. And this also would have been about a couple of meters tall. If you look at them in the picture, you don't see much. You think they are random collection of stones. But if you go back and simulate the movement of the sun and the moon over 1 year in this observatory, you find interesting things. The black colored objects are all shadows of stones calculated as per the height of the stone. So, taking based on the height of the stone, you will see that it's winter or summer, how long will the shadows be. So, the left is the west, the right is the east. So, the stone here is sufficiently large so that during sunrise, the shadow would go all the way over here. And so on. So, there is a small stone here, there is a large stone here, and so on. And the red lines indicate points where the shadow of one stone touches another stone. And because the situation is similar, if you have similar size stones over here, then at summer solstice sunrise you will get this shadow. At winter solstice sunset you will get this shadow. So essentially, you get a set of about nine, what, three and three, about 10 stones, which are put there in such a way that the shadow of one stone touches another stone, and you have 10 confirmatory data with which to confirm that the winter solstice or summer solstice has arrived. That is how accurate, that is how much effort went in putting in these stones in such a way that they would give you markings for winter solstice and summer solstice. And early poetic literature from India is obviously Rigved, and Rigved says that look, just as the quest of a peacock is this jewel. Just like the comb of the peacock or the querist shell on a serpent, Jyotisha, astronomy, is the head of auxiliaries of Vedas. It is like the greatest among the auxiliaries of Vedas. So Vedanga literature, among the Vedanga literature, Jyotisha is the best and the most important. Um, so what does Rigvedic astronomy consist of? Rigvedic astronomy consists of two parts. The first is Vedang Jyotish, which is actually a very systematic, objective, mathematical study to determine the sunrise time, the sunset time, the moonrise time, the moon phase of the moon with reference to a given day, the exact location of the sun or the moon in the sky on any given day, etc., to determine the time scale and all. It also mentions nakshatras, it also mentions how to calculate the day. It knows that the day is 360, a year is 365 days long, a little more than 365 days long. Not 366, but not 365, but somewhere in between. And it knows that the lunar year is only 354 days, while the solar year is 365 days and a little bit more. So, how do you synchronize the two, etc.? All those kinds of discussions are there in Vedanta Jyotish. And then the basic literature of Rigved itself also is there. Now, the problem with Samhita is that these are written in very poetic styles with lot of ambiguous language and a lot of freedom for creativity. So it is not always possible to put down exactly what was being referred to in the Samhita at any given time. Vedanta Jyotish is very clear, very specific, and very geometrical in its discussion. But Samhita has various literature, and they are scattered all over the place. Um, Lokmanya Bal Gangadhar Tilak, one of our great freedom fighters, actually spent a lot of time in jail for his participation in the freedom struggle. He was a student incidentally of Deccan College where he had learnt archaeology, and he was a Sanskritist. So he sat down in this long incarceration in the jail. He would sit and read the Rigved again, and he would think about it, and he would think of astronomy. And eventually, he concludes that Orion is a very important constellation. Orion or Mrugashirsha is a very important constellation in Rigved. And then he goes on to show various references to Orion, Taurus, and Pleiades combination. The same thing that I showed you in the supernova, incidentally. So it shows Orion, Taurus, and Pleiades in great literature. And because the vernal equinox species, he shows that the earliest references are to vernal equinox in Canis Major, which is to the further west of Orion, and then it comes into Orion, then it comes into Taurus or Rohini, and then in 2000 BC it is recorded in Pleiades. So, because Rigved refers to vernal equinox in Canis Major, Orion, Taurus, and Pleiades, which is 6000 BC, 4000 BC, and 2000 BC, Tilak concludes that the astronomical references to Orion, Taurus, and Pleiades and vernal equinox go back to as much as 6000 BC and as late as 2000 BC. So it has a memory of this 4000 years of drift of vernal equinox within its literature. Even though Rigved itself is written down around 1500 BC, it has very clear reference. It has the reference in 2000 BC is very clear. It very explicitly says that the Kritikas do not move from the east. But as you go further back in time, the references become a little more weak, a little more poetic. The people who wrote it down finally had some vague idea of what the original poem was, but probably not as confident. So there is a degree of vagueness. The further back you go, the further vagueness. The literature becomes a little more vague, but clearly there is a reference to this. So that despite being vague, there is a discussion of the dog barking to start the year, and that is vernal equinox in Canis Major, and then the Mrugashirsha itself is called the day of the year, because that is when the sun, 4000 BC, that is where the sun was passing through Mrugashirsha to begin the year. The vernal equinox was there. So these kind of references are in ancient literature. Both Rigveda and Yajurveda have their own Vedanga Jyotisha. This is dated to about 1400 BC, and that is essentially for timekeeping. So they have discussions about the length of the day, the length of the year, how to measure the daytime to nighttime ratio during winter solstice. So it is 1 is to 2. So the night is twice as long as the day at one winter solstice. If you go further north, it becomes 1 is to 3, and so on. And eventually, of course, if you go to the poles, it is 1 upon 0. So it is infinity, because there are days when the sun, on one winter solstice, the sun will not rise at all. But there are discussions like this which are there in Vedanga Jyotish, and which is probably the earliest scientific document, because it discusses nakshatras, it discusses constellations, it discusses the suns and moon movement through these constellations, and the whole early astronomical work. Division of sky into various constellations comes up. You can see that each 30-degree region is divided into various regions, and you have the various constellation names. They are seen in Babylonia, which is 3000 BC. Greek names are relatively recent. Early Indian names are from Vedanga Jyotish itself. And then Varamira 500 BC. So this is Babylonian mean 3000 BC. This is 1400 BC. This is 500 AD. Greeks are 700 BC, and English equivalent, of course, is very modern. But you can see these 13. The sky is divided into 12 parts of 30 degrees each, and that is how you get your 12 zodiacal constellations. Then you come to third stage of astronomy civilization, and there you can see that now astronomical myths become much stronger. Astrology enters into field, whether these planets, etc., and their movement can tell you about your future or not. They cannot. Astrology is complete nonsense. But at least people try to see if it made sense, and I can assure you it doesn't make sense. And then new and interesting cosmogonical ideas also come up about who we are, where we are, and so on. In the absence of other knowledge, astronomers then become a great center of focus. Many of the creation myths and many of the older astronomical myths are actually rewritten. Rahu and Ketu, who were originally demons, now become 2 points in the sky, and you calculate saying that if the sun and the moon both come to either Rahu or Ketu at the same time, then you get an eclipse. And because that Rahu and Ketu point can be calculated, they become dark planets in the sky and so on. So old myths are rewritten and reevaluated. There is an interesting mixture of religious beliefs, astronomy, and architecture that emerges at that time. And I will show you temples are a very classical example of astronomy on Earth. Some amount of mathematical astronomy comes in at this stage because people start calculating movements in detail, especially if you want to do Kundali and stuff like that. You have to be able to calculate planetary motions and so on. The great civilization in India at the earliest time is Harappan civilization, dated to about between 2500 and 1700 BC. And there is a city called Dholavira, which is exactly on the Tropic of Cancer in Gujarat, about 100 kilometers east of Bhuj. And there is a town called Dholavira. That Dholavira was one of the largest towns of Harappan civilization. It probably had a population of something like 25,000 people, and it was at the southern end of the civilization. So a lot of products and finished products would come along the great rivers of the Harappan civilization, carrying their material, which would then be taken at Dholavira, either polished, improved, etc., or even just shipped, and it would be shipped to West Asia. So Harappans had a flourishing trade with West Asia. So you could see this material going through this Dholavira. Dholavira is in a little run of Kutch, so water was an issue. So they have elaborate water storing systems, but I don't have time to go into that. We have the Tropic of Cancer right at Dholavira, and therefore their summer solstice day is their zero shadow day actually. During the Harappan time, the run was filled with water, and hence boats could move from there. And like I said, it's exactly on the Tropic of Cancer, which is important. So there they have odd structure. There's a structure that looks like this. And for Harappan who knew architecture very well, this cannot be a mistake. The other point is that this line points exactly to the north. So you can imagine if I build a hut on top of this and put a slit in the ceiling, then at the summer solstice, the sunrise would be over here. Then, as the sun starts going south, the shadow will start going north, and you will have sun in various regions. So you will have July over here, August, September, October. You will get the equinox day, November, December, January, November and December, and then it will start forming back again. January, February, March, April, May, June, July. July it would come back here. So just a plank on this would sort of give you the complete calendar. And the gap we suspect is because at the winter solstice, when the sun shadow went, when the shadow of the sun from the slit would keep rolling along this line, and because of the thickness of this wall, when it crossed, it would essentially jump and touch this side. So this depth and this width were exactly calculated so that the shadow that was seen over here as it crossed would go and touch this to give you a second confirmation that you had actually reached winter solstice. And then it will move along this direction from day to night. There's another structure exactly orthogonal to this that also does similar things in the same region of Dholavira. So we think Dholavira had a fairly sophisticated solar observatory. This is what I meant at winter. So at summer solstice, the shadow would simply go through the center and come to the edge. But at winter solstice, as it passed through the top region, the shadow would jump and fall at the back and then roll over. So we think that this is an observatory, and which is what you would expect. The other interesting feature is that by 700 BC, in the Gangetic Plain, the kings start making coins. So they take little metal pieces and they they mark with punches on that as their currency. And the currency would be, of course, specific to a king or a kingdom, and it would have a certain value. And these were metal bases. So you had all kinds of patterns on these things. These are typically a few millimeters in size, a couple of centimeters in size. And you can see that it has various markings of dots and circles and some things that obviously look like sun, but the others are more interesting. The more interesting ones are a little different ones. You get a whole series of observations of this kind and a whole series of observations, coins of this kind. So these coins clearly show that they are talking about something in the sky. Pleiades is known to have 6 or 7 stars depending on which era you look at, because these stars are moving with respect to each other, so some of them may be occulted at any given time, and therefore you can't see 7 all the time. So 6 or 7 stars are commonly referred to as in Kritika, and you have 5, 6, or 7 dots. The interesting thing is the center thing here. So here you have Kritika or Pleiades, and here you have the moon. Now, moon and Pleiades conjunction happens only once in 18 and a half years. And at that time, moon may be full moon or partial moon or whatever it is, depending on that particular cycle. So this event is a very rare event. It happens once in 18 and a half years, and we think all these are markings of that. So stars have been referred to as toads and so on, but these are clearly a partial moon with the Pleiades in between. So even in these little 2 centimeter size punch mark coins, people have been marking astronomical events, especially rare events that take, like I said, 18 and a half years to repeat. Then by now, cosmogonical ideas become more sophisticated. There is Brihadaranyaka Upanishad, which says that the universe consists. So there is a discussion between Gargi and Yagnavalkya in Brihadaranyaka Upanishad. And Gargi asks Yagnavalkya as to what is the world surrounded by. He says everything on earth is surrounded by water. Everything in the water is wrapped by air. Everything in the air is wrapped by the sky. Everything in the sky is wrapped by the world of Gandharvas. And planets were referred to as Gandharvas. And the world of Gandharvas is wrapped up in the world of the sun. The world of the sun is wrapped up in the world of the moon. The world of the moon is wrapped up in the world of nakshatras. The world of the nakshatras is wrapped up in the world of the sun, devas. The world of the devas is wrapped up in the world of Indra. The world of Indra is wrapped up in the world of Prajapati, and everything is wrapped up in the world of Brahman. And when Gargi says, "What about the beyond the world of Brahman?" Yagnavalk simply loses his temper and tells her to shut down. But if you forget this world of Devas, Indra, Prajapati, and Brahman, up to this, the first 7 points are reasonably accurate if you are living in an island or even in a continent, you would see the seas on either side. Except, of course, the moon is wrong. The moon should have come after the sky, and the planet should have come after the sun. But generally, the idea seems to be pretty reasonable. So this kind of ideas happen about what the Earth is, where we are, what relations are there, and so on. Also, various cosmogonical ideas come up from Nasadiya Sukta and so on. Then Ajanta and Ellora caves, for example, they are in a U shape. So you would think that they are not really astronomically minded at all, except, sorry, when you look at these caves, you notice that they are not exactly aligned along the curvature. They have been sort of partly distorted and all that, and you end up with an interesting map. So what I have here is the angle with respect to the sun. So during sunset, winter solstice sunset is over here, summer solstice sunset is over here, winter solstice sunrise is here, winter solstice sunset is here, and you have the cave number over here. And you notice that these caves are all toward the equinox. These are the oldest caves. Well, these near caves seem to record sunrise point at between winter and summer solstice on different days. In fact, two of them are tuned to pick up the sunlight, summer solstice sunrise. Others are designed to pick up equinoxes and so on. So even in this apparently circular cave, there seems to be some kind of orientation according to astronomy. Ellora, you would think, is exactly on a mountain which is exactly east south, east west, and therefore you would think that it has no sensitivity, but it does. So the caves again are slightly oriented, so they can largely pick up the summer solstice sunrises. As many as five or six caves come over here. So clearly, sorry. So that okay, this is the lower part right now over here. At Ellora, which is exactly east-west mountain, you can see that they all pick up the sunset point at winter solstice with varying degree of accuracy. Only one cave is not solstice sensitive, but the other one will give exactly winter solstice. Several pick up summer solstice, and the other will pick up the equinox day. You can actually see these sunset markings, and the caves are slightly angled to achieve this. Then temples. Temples are a curious thing. Temples essentially arise originally from structures that were made to honor the dead, and eventually from original megalithic astronomical observatory, and everything gets confused. So, what is a temple? A temple is where gods come and reside, and where you pay your respects to gods. And there are basically two styles of temples in India. These are called the Dravidian styles of temples, where you have large Dwarpalas, but the Garbhagriha is not very conspicuous. And this, of course, is Meenakshi. And you can see that these are exactly north, south, east, west. And then in northern India, you have temples which are called Nagara style, where you actually have three chambers. You have the chamber in which the god himself sits, the internal Garbhagriha. Then you have one hall where the kings used to sit, and the second hall where the common people used to sit, and various discourses, etc., would happen in these temples. But the central temple structure is fairly interesting mix. It is, the temples in India start with around 500 BC with the spread of Buddhism. The Hindu priests also adopt the idea that if you have a centralized place of worship, then it is easier to keep your people together. So they come up with the ideas which are in response to the Buddhist stupas and a mix of memorial stones. So they are essentially originally memorial, which will then become known for worship. So the idea of temple comes in but in order to make it more connected with the heavens, the orientation of the temple is very peculiar. So this is the north on the top, south is the bottom is the south, and you have the east and the west, and you notice that specific gods are supposed to hold specific locations. So the Brahma sits in the middle, the great heaven sits in the middle. And then you have Surya in the east coming in, the Varuna comes in the left, Asuras come on the northwest, and so on. Sugriva comes in southwest, etc. So the idea, this is heaven on earth. This is the idea that the sacrosanctum where the god sits is actually a representation of the sky on earth. And that is how you have temples which are originally designed with that gnomon in as the first structure, and then the rest of the designs are made because the exact north south east west has to be maintained because the image from the sky on the earth has to be maintained. And so then there are other oddities that come in. So there is Ursa Major, etc., where there's a a rough reference to Ursa Major as being a calendar. We know Ursa Major or Saptarshi doesn't move in the sky, but when you simulate the exact movement, it turns out that the Saptarshi is this vector of Saptarshi, the pole to the first two stars of Saptarshi actually point to a specific location in the sky, and therefore that calendar once made sense. Based on this, you can date various ancient literature. You have Rigved, which is referred to 6000 to 2000 BCs by Tirak. You have Bruhat Samhita, which actually has memories of events 5000 years ago. You have Yajurved, which is dated to 2350. You have Yajurved Vedang Jyotish, which is 1370 BC. The period of Lagada is 1340 BC. Mahabharata is dated to 1200 BC from the Saptarshi calendar I just showed you. And then you have Parashar Samhita, which also talks about seasons, and that can be dated to between 11 and 1300 BC. And then you have the fourth period of astronomy, the technology-based astronomy, which is where interesting things also happen. So now astronomy becomes highly specialized. The education is specified. You have to be qualified astronomer and so on. And it is largely driven by mathematical astronomy. And astronomy grows with various people. So this, for example, is a map of how to go from one point to another in the sea where there is no land reference. So if you go to Mumbai and say you want to be smuggled into Dubai, those fishermen will pull out a chart like this for Mumbai and say that if you want to go toward Dubai, you have to move along, say, this constellation or this constellation or this constellation in the sky for 3 days, and then you will reach at the next port. You pick up the similar map from the next port, and then you follow the constellations in that next port, and eventually, after a fixed amount of time, you will reach wherever you wanted to reach. And they have a way of measuring whether the speed is correct or not, and so on. But star-based sky map was commonly used by fishermen to go from one point to another from earliest times. In India, this period is called the Siddhantic astronomy. Siddhanta is basically based on mathematical astronomy. And the phase starts at 500 AD when Aryabhatta starts writing mathematical astronomy. And Aryabhatta says that, look, I'm not writing, all that I'm writing is not my creation. My work is more encyclopedic. So Aryabhatta is an encyclopedic volume consisting of all the astronomical knowledge at that time. And he explicitly gives his date of birth. So we know that he was born in 500 AD. And over the next 1000 years, the preoccupation of Indian astronomers then becomes calculating planetary orbit using geocentric calculations and so on, which are not so easy to do. They develop various algorithms and they come out with trigonometry. So this is mathematical equations become important. Sine function comes in, eclipse calculations come in, Rahu and Ketu, and I'll show you how this is done. So sine function comes in because the sun does not move uniformly in the sky. It becomes slower as it moves towards the pole or towards sunset or sunrise, and moves very quickly in the sky in the daytime. So the first sine function was defined at that time and then calculated. The sky is divided into 360 degrees because 360 degrees roughly make a year, and therefore the sun moves to 1 degree per day and so on. So that 360 number comes from there. Then, because of the fact that the Earth is moving like this, you end up defining a celestial sphere where you take your the path of the movement of the sun as a circle. the spring equinox is your 0 point, and then you can determine angles to any star. So you take the path of the sun, the ecliptics, as the great circle, the spring equinox as the 0 point, and then you have a complete coordinate system. You have right ascension and declination points, and you can calculate the location of any star in the sky. So you have right ascension and declination. This is the celestial equator along which the sun moves, and then your north celestial pole and south celestial pole, and the sun moves like this, and you can determine the right ascension and declination or the coordinates of any star in the sky. So declination, you have declination, which is this angle with respect to the vertical. You have the right ascension, which is the angle from vernal equinox contact point or the exact east, and then you can calculate the coordinates and time and place of depending on where the sun rises compared to where Ujjain. Ujjain is the zero latitude at that time. You can determine the entire coordinate system of Earth and the sky, and then vernal equinox is the 0 point for the sky, and you can make these calculations. And then you have geometry of spheres. You have to, of course, use this complicated cosine rules for calculating distance between stars and so on. I'm not going to spend time on this because there are other things that you just need to memorize. There's an equation of time. The equation of time describes the discrepancy between two kinds of solar motion. The apparent solar motion, which is simply 360 days divided by the number of days since equinox. But because of the fact that the Earth's orbit is elliptical, the sun does not move uniformly in the sky. When we are closer to the sun moves slightly faster than when we are away from the sun. So one is apparent time, average solar time, and the other one is mean solar time, where the sun would be off 24 hours later. And the equation of time essentially corrects this. I'm sorry. Okay. I'm sorry for the animation error. But you have this, so you have the ellipticity of the orbit, 23.5 degrees. Sorry, this is the fact that the sun is at one of the foci of the ellipse is slightly extended. This you have the obliquity, 23.5 degrees angle. And these two get added. And these two get added to give you the equation of time, which on Earth looks like this. If the Earth were to become vertical, the 23.5 degree angle was to be lost, you would have only this curve. If the Earth was to continue 23.5 degrees, but the orbit was to become completely circular, then this would become flat. But together they give you an interesting diagram over 1 year. So if you were to photograph the sun at the same time every day, you would not get it in a straight line. You get it in an odd shape of number 8 in English numerals, and these are the equinox point, and you will get, depending on which part of the Earth you are on, somewhere this will be bigger, somewhere this will be bigger, but you get this NLMA, which is planet specific, and you can from this itself calculate the speed with which the Earth moves when it is closer to the sun or away from the sun. You can imagine this is when the sun is longest in the sky. So it is summer solstice, this is winter solstice, this is equinox, and so on. And then you have planetary motion, which are difficult to keep track of. So the inner planets essentially rise with the sun or set with the sun. So they are inner planets, they become morning star or evening star, Mercury and Venus. The outer planets, and I'm sorry, I don't have that image, are in fact have retrograde motion and forward motion. So, and I've had that image somewhere, I don't know where it is. Okay, I'll come to that a little later. But there is an interesting problem that happens, that if suppose the sun is here, with respect to a distant star, the star is like that. By the time you come to the same star location, the moon has moved over here, and the sun has also moved. So the sidereal day that you get, where the moon points to the same star at night, is actually 27.5 days in the star rise and so on. So there are various years are defined, where you define tropical years, where the sun moves to the vernal equinox. 0.24, you can define sidereal, where the sun returns to the same star or the moon moon returns to the same star that is slightly longer. Anomalistic year, which is the time between two succession passes through perihelion or ephelion, and that can again be the same length as nearly the same length as synodic day. Then you have synodic period and you have draconian period and so on. So there are subtle differences on the calendar depending on what is the axis of rotation reference you take in the sky. If you take the sun, if you take the full moon, if you take distant stars, each of them has a different thing. And then this is the retrograde motion of the outer planets that I was talking about. That slide should have been here, where you can see that if the moon Mars orbit is here and if the Earth's orbit is here, with respect to distant stars, the moon will seem to appear and then go retrograde and then back again. And while calculating the orbits of planets, obviously retrograde motion is a huge headache. And because they had a completely geocentric, Earth-centric system, they didn't know how to account for it. So they come out with this idea of epicycle, where the Rahu and Ketu, I've already told you, are the one of the Navagrahas. I'll not go into the story of it because I'm already running late. But I'll just tell you how Rahu and Ketu are calculated. So, Varamira onwards, people are very clear. In fact, Aryabhat himself is very clear that the eclipses are simply shadows of Earth and Moon. Earth on Moon for lunar eclipse and Moon on Earth for solar eclipse. And so what they do is they know that the diameter of the sun, they know the sun finishes 365, it takes 365 days to do 360 degrees. The moon diameter we know, and you know it takes 27.5 days for 360 degrees. And therefore you can calculate their points. You then calculate Rahu's period. When it's a point where if sun and moon both come together, then you have an eclipse. And you know that this angle is like 5 degrees from the ecliptic. You know this is, and this period comes out to be 18.5 years. That is how we know that the eclipse patterns repeat every 18.5 years, and it's called Saros cycle. But you end up calculating Rahu and Ketu as dark points because otherwise how do you calculate eclipses? And the simplest way to do it is to keep track of this movement of Rahu. Then we have Panchangas, which are essentially Varas, Tithis, Nakshatras, Yoga, and Karna, which makes the 5 points of the Panchanga, five elements of timekeeping. Out of which Yoga and Karna are something we don't use, but Nakshatra, Tithi, and Vara we use. So solar Vedanta Jyotish itself tells you how to calculate nakshatras and whether the sun or the moon is in the nakshatra and so on. And Panchanga means 5 limbs, and they are used, as I told you, in various ways. Then Tithis are the essential the dates of lunar calendar, which Tithi the moon is in. And those calculation of Tithis is done. Varamira shows how to do it. Surya Siddhanta is the book that defines that. And we have shown that there is a problem in the sense that if you look at the path of the moon today, it is very far from the nakshatra point. So the nakshatra conjunction star that was defined is now nowhere close to the path of the moon. And so the argument was that, look, sometime in the past they may well have been together. So what we did was we calculated the average distance of the moon from all the nakshatra points that are defined. And it turns out that between 3000 BC and 2500 BC, the moon was closest to all the nakshatra points. So we suspect that the nakshatras were defined between somewhere between 3000 and 2500 BC. And that is why we have these nakshatras which are today at odds. Today they are dispersed, but once upon a time, they were 2500 BC or so, they were really very close. Varamira, incidentally, also defines who can be an astronomer. And his definition of an astronomer, interestingly, says that he should know the time division, he should know the planetary calculations, he should know terrestrial calculations, etc. Interesting is he is not expected to know astrological requirements. Astrology is not an Indian field at all. It comes to us from the Greeks, from the Yavanas, and it is never taken seriously. So no great Indian astronomer is involved with astrology. And because astrology makes no sense, it's obvious that it makes no sense. So astronomers who were in the service of the king had no choice, so they would make these kundalis, etc. But no serious astronomer believed in astrology, and it's worth remembering that. It's not an Indian subject. It comes to us from the Yavanas, from the Greeks. And then astronomy of the Mughal period, where horoscopes are cast and astronomy is done with great precision. People set up calendars of various kinds. I'm going to sort of jump through these, they make these astrolabes, which are very, very impressive. These are Arab constructions where you have the azimuth, you have the so this astrolabe has to be made separately for each location. And so Polaris is over here, and depending on where your latitude is, it could change accordingly. So and using this, you could actually accurately calculate your date and time um, based on these astrolabes. And there are Sanskrit astrolabes also, which are essentially the technology was brought from Arabs and eventually it was created here. You have Jantar Mantar by now, which of course is designed to keep track of the motion of the stars and planets in great precision. Again, I'm going to skip this. Astronomy today is modern astronomy. It is full of multi-wavelength, above atmosphere, high-quality telescope astronomy, and it also mixes physics with it, which gives you the astrophysics subject of it. But I'm not going to talk about it for obvious reason. That is very modern. So astronomy can be divided into four parts: the initial phase astronomy, the settlement astronomy, the astronomy of civilization, and technology-driven astronomy. And if you go back and plot the sophistication level of sophistication of astronomy of each culture against the years since they are settled, it turns out that it fits a beautiful linear curve. The longer you are settled, the more sophisticated is your astronomy. So you get a clear calibration curve that if you know how sophisticated culture is, you will know how sophisticated their astronomy should be. So basically, what I'm trying to say is just to wind up in two slides. Astronomy has in India is 550,000 BC to 5000 BC. Settlement astronomy is 5000 to 2500 BC for Harappans and 1500 BC for later Vedic period. Astronomy of civilization is 2500 to 1900 BC and then 1500 BC onwards for Upanishadic and Puranic period. Technology-based astronomy is Aryabhatta onwards. The bottom line is astronomy can be used to map the intellectual growth of a civilization. There are distinct phases which you can identify. And while archaeological evidence does not show these dramatic changes, you can use archaeological data to understand the intellectual growth of a civilization based on their astronomical knowledge. Thank you very much. If you have any questions, you can ask.
Thank you, sir, for
I
your
will stop.
wonderful lecture. Uh, you very well covered the phases of astronomy from early historic, I mean, archaeoastronomical periods to the modern astronomical period. And I wonder the focus and shift of people from early
Yeah.
prehistoric people to our modern civilization changed drastically. Earlier, people would have
Yes, sir.
more time in seeing stars, constellation, and observing it. Now, as the civilization progress, astronomical progression is there, the the science center which is involved in public publicity of science as well as astronomy to more public spaces, I mean more to public, we see that uh, because of the complexity or something, the more usage of gadgets, TVs, etc. The focus has been shifted and less time has been devoted to observing stars and skies. It is actually some is focused on a little bit conglomerate of people, where the larger public is not well giving time to observing things, etc. But then it's a wonderful lecture, sir, because you have covered
Mm.
a larger topic. In fact, how the astronomy evolved from the the historical prehistorical period to the modern astronomy, and how these calculations were made, etc. Were very much interesting. In fact, it is very useful to
Thank you.
students also. And I request if the participants have any questions to ask, they can ask. They can put it in the chat box, so we can have the question and answer session now. Or even if you have something to ask, I could share our email address also. I will deliver it to sir, and
Yeah,
he
sure.
will reply to
Yeah.
the
So if you
questions.
can't ask now, please feel free to write to me. on my email address, and I'll be happy to answer the
Yeah,
questions.
I will share our email address also, so
Sure.
the participant can
Yes,
ask
sir.
questions and they can get answers from sir.
It would be my pleasure.
If anybody would like to ask some questions, please do it immediately so that we could wind up the session. Okay, I think they will share it through the email.
Yeah,
And
sure, sure. Yeah, YouTube live. Is there a
so
question? Okay.
they're telling us it's very informative, very nice scientific
Okay.
explanation, etc. But not asking
Thank
questions.
you. Thank you very much.
Okay.
Yeah, please feel free to write to the center, and I'll be happy to answer all the questions.
Yeah, yeah.
Okay?
So once
Yes,
again,
sir.
thank you, sir.
Thank
Once again, thank you for all the
My
participants. We
pleasure.
will wind up the session, and we'll continue with similar sessions in the future also. And thank you, sir. We will end the live session, and thank you
Yes, sir.
once again.
Thank you. Yes.